Hi guys, in this session we're going to do the 2014 VCAA Maths Methods Exam 2 paper extended response questions, questions 3 and 4, and in a part 3 video we're going to do question 5, which is the grand finale in more ways than one. So I hope these questions help you today. My work solutions of them, and remember that my work solutions are just my unofficial solutions, and I hope they help. Alright, question 3. In a controlled experiment, Jan took some medicine at 8 p.m. The concentration of the medicine in his blood was then measured at regular intervals. The concentration of medicine in Juan's blood is modelled by the function da-da-da-da. A very interesting little function. We've got some t trying to make it go up, and some e to the minus 3t on 2 trying to make it come down. And so it does a bit of both, and it has a hump in the middle. T is greater than or equal to 0, of course, because t would be time. C is concentration of medicine in his blood, milligrams per litre, t hours after 8 p.m. Alright, that's the graph down there, we get that. Okay, it looks like a nice little question, guys. Probably a bit of CAS in here, a bit of fiddling around with various parameters in the graph and times and concentrations and things. What was the maximum value of the concentration of medicine in Juan's blood in milligrams per litre, correct to 2 decimal places? Probably a case for CAS, I would say. It's a 1-mark question. All they want's the answer, so let's go for it, guys. We would put the function into the handheld, we would take the derivative, set it equal to 0, solve that for t, and then plug the value of t back into the function to get the concentration. Var she be. So we've got here, what do we got? We're putting this into the function, and that's happened there, and now we're solving it for the derivative being equal to 0, and we got a value of x, or t I really mean, but I'm putting x in here because it's more convenient. X is 2/3 of an hour. When we get a maximum, or the derivative equals 0, which is the maximum in this case. Alright, so next step, we then plug that value of t in back into the function, we get this, and we're asked for a decimal approximation, and therefore we get that, and just to finish it off, to 2 decimal places, 0.61 milligrams per litre in Juan's blood. Jolly good, that was nice and easy. Let's go for the next bit. B1. Find the value of t in hours, correct to 2 decimal places, when the concentration of medicine in Juan's blood first reached 0.5 milligrams per litre. Well, that's alright, no problem. Let's do that. That's 1 mark. Nice, easy question. Use CAS. So we solve for when the thing equals 0.5 now. That's when the function, the concentration function, equals 0.5, and we get these two values. That's on the way up, that's on the way down. So we want on the way up, don't we, when it first reaches 0.5 milligrams per litre. And how many decimal places do we want? 2 decimal places, right? So that'll get us that. No problem. 2 marks for us. Jolly good. Next part. Find the length of time that the concentration of medicine in Juan's blood was above 0.5 milligrams per litre. Above. Oh, well, that's just going to be between here and here, isn't it? Oh, nice and easy. 2 marks for us. So therefore we get those two values as we got up there. Yes, and then we just got to subtract one from the other. And 2 decimal places. There's a little graphic to help you in case you haven't quite got it. There and there, and we want the delta t, this span in here, yeah? So that's going to give us 0.86 to 2 decimal places in hours. Well, no problem so far, very cruisy. Next part. What was the value of the average? Now they're testing our ability to know what the average rate of change is. Average rate of change of the concentration of medicine in Juan's blood over the interval 2/3 of an hour to 3 hours. Express the answer in milligrams per litre per hour. That's right, correct to 2 decimal places. Well, we've just got to take the value of concentration at 3 hours minus the value of the concentration at 2/3 of an hour and divide it by the time which elapses between 2/3 of an hour and 3 hours. No instantaneous derivatives in here, guys. Just basically just delta C over delta T. That's what we're doing. Yeah? Okay? Did you know that? Hope so. There you go. So the average rate of change to 2 decimal places would be minus 0.23 milligrams per litre per hour. Yeah? No problem. Still pretty cruisy. At times T1 and T2, the instantaneous rate of change, that is the derivative of the concentration with respect to time, of medicine in one's blood was equal to the average rate of change. Oh yeah, okay. So that's just a CAS thing. Find the values of T1 and T2 when the instantaneous rate of change was equal to the average rate of change. No problem. So dCdt is going to equal the thing which we just worked out there, and I think we can, it's a 2-mark question, we can just go for the CAS, and we can just do this. Oh, it looks a bit nasty, doesn't it? Gurk. So what have I done here, guys, before you all panic? So that's the derivative of the concentration function. I've set that equal to the average rate of change, all right? That's what I've done there. And it comes out to be a beastly looking mess, okay? So why did I do that instead of trying to solve the whole thing for when the derivative equaled the average rate of change? Reason, guys, is because I probably got an unholy mess, and it's easier to make a mistake if you try to do too much at once. So I just state this equal to that, I get that, and then I do a history recall of this answer here into the next working line, and then I do the solve there. So solve for that equals to that for the variable we're interested in, and it's much easier to do. So there's a little tip for you. You might like to break things up into 2 steps instead of trying to do everything at once and then just getting it all messed up, because after all you are under a little bit of stress because it's an exam situation that you would be working in. Alright, and we got this. Okay, so what was the values of T1 and T2, 2 decimal places, 0.90, 2.12, and that would be there. Very excellent. They are the times, T1 and T2 in hours, alright? Alright, next bit now. Alicia took part in a similar controlled experiment, however she used a different medicine. The concentration of this different medicine was modelled by that function, which looks pretty similar to what we had, except we've got an A and a K in there. And it looks like they're positive reals. Okay. If the maximum concentration of medicine in Alicia's blood was 0.74 milligrams per litre at time t is 0.5 hours, find the value of A, correct to the nearest integer. So this is a 3-mark question, and they're amping up the difficulty level here a bit, guys. You'll notice we've gone all a bit abstract here with pronumerals everywhere. This usually causes a bit of a panic reaction. But look, don't panic. Just think about what it is we've got here. You've got 2 variables. You've got A, you've got K. Therefore, you need 2 clues to give us 2 equations to solve, okay? And probably we're going to be using CAS here. We can do the setup statements and then we can do the solve with the CAS. The setup statements are probably worth a mark each, and then the answer mark with the solve is probably worth the 3rd mark, I would suggest. So come on, you know what the clues are. Read the question again, get the clues. First thing you know is that, okay, the concentration is N this time, not C, and at 0.5 hours it's 0.74. This is the equation, so plug in everything you know. So the only things that are unknown now are the A and the K. That's equation 1. Now what is the other clue that you've got? What is the other clue? Well, we know that here we are we haven't used the maximum concentration, okay? That is the concentration, but we know it's the maximum, so we can take the derivative and set it equal to 0, can't we? Of course we can. So therefore we've got that equation there. Now, there's 2 equations, 2 unknowns. We can solve them, and I suggest we probably use the CAS just to avoid pain and anguish trying to do them by hand, which would be ridiculous. Correct to the nearest integer. See, that's always a clue. They don't want an exact answer. It's probably better on CAS. So here we go. Here's the equation. Hang on, what am I doing there? I'm putting the concentration function into the calculator. Now I'm solving simultaneously for the concentration at 0.5 hours equals this, and for the derivative of the concentration equals 0, given that x, or we really mean t, but we're using x is 0.5, and we're solving for A and K. And look at that. So which one did we want? We wanted A, correct to the nearest integer, so the answer would be 4. There you go, guys. Not too shabby at all. Now, question 4. Patricia is a gardener. She owns a garden nursery. She grows and sells basil plants and coriander plants. Okay. The height in centimetres of the basil plants that Patricia is selling are distributed normally, okay, normal distribution, with a mean of 14 centimetres and a standard deviation of 4 centimetres, and there are 2,000 basil plants in her nursery. Goodness, that's a lot. Patricia classifies the tallest 10% of her basil plants as super. What is the minimum height of a super basil plant correct to the nearest millimetre? And this is a 1 mark question, guys. Have a little think, get your head straight, and it's very easy. We're dealing with inverse normal on the CAS handheld, aren't we? We want the minimum height of the super basil, okay? So therefore we just want inverse normal. We're going from the probability back to the height. We've got the probability is 0.9, that's the minimum value of a super basil. We've got mu is 14 and 4 was the standard deviation. We can easily plug that into the CAS and we'll get that answer. And this is the first trap of question 4. This answer is in centimetres, guys. And we're asked for the answer to the nearest millimetre. So there you go. You've got to watch these guys. That gets us 191.26 millimetres, which, if we're quoting the answer to the nearest millimetre, would be 191 millimetres. So, well done to you if you spotted that, and watch it if you didn't for when you're doing the exam, and well done, Patricia. Over the screen we go. Patricia decides that some of her basil plants are not growing quickly enough, so she plans to move them to a special greenhouse. She will move the basil plants that are less than 9 centimetres in height. Okay. This question says, how many basil plants will Patricia move to the greenhouse? Correct to the nearest whole number. Well, guys, we need to know the proportion of the basil plants that are less than 9 centimetres in height. So that sounds like a normal CDF to me. What about you? Yes, and then once we get that proportion, we can multiply that by the number of her basil plants, which is 2,000, and we'll have our answer, and then we just correct it to the nearest whole number. No problem. 2 mark question, easy as. So normal CDF, here we go. Lower bound is minus infinity, upper bound is 9 centimetres, 14 and 4 as we had before, and what proportion do we get, guys? There it is. There it is. So it's that thing, and if we multiply that by 2,000, we get that, and to the nearest whole number of plants, we've got 211 plants. There you go. She's got to shift 211 plants into her special greenhouse. Alright, over the screen. Now we've got some coriander plants now. So the heights of the coriander plants, x centimetres, follows a probability density function. So this is not normal distribution now, it's just a probability density function, h of x, where h of x is a trig thing. Okay, no problem. State the mean height of the coriander plants. Well, I always like to get a bit of a feel for what this is doing here. Now, come on guys, let's work out the period of this thing. It goes from 0 to 50 centimetres high. 2 pi over 50 gets us 100. So the period of this function is 100. So okay, it's a sine function. So we've got the first half. We've got the humpy bit that's above the central axis. Yeah, okay, I'm happy now. Let's move on. The mean height, 1 mark. Okay, oh no problem, just go for it with the CAS, guys. It's very easy. Use CAS, and we're putting this function into our calculator, and then we're just going for the formula for the mean, which is the integral of x times f of x with respect to x from 0 to 50, and we get 25 centimetres high. That's it, exact answer required. Alright, very good. Patricia thinks that the smallest 15% of her coriander plants should be given a new type of plant food. Probably a good dose of fish oil might do it, or seaweed. Find the maximum height correct to the nearest millimetre of a coriander plant if it is to be given a new type of plant food. Alright, this is just a straight probability density function kind of calculation. So what we can say here, for 2 marks, we can do our setup statement here, and we can say that h of x, the integral, from 0 to h, and that's the one we've got to solve for, guys, of this function with respect to x gets us 0.15. So we can solve that easily with the CAS, and we just go straight for the jugular. We solve for the integral of the trig function with respect to x equals 0.15. We're solving for h from 0 to h, and given that h goes from 0 to 50 inclusive, you have to put that statement in, otherwise you'll get a general solution because this is a trig function and you'll get a big mess. We're dealing in centimetres and they're asking for the answer to the nearest millimetre. So let's multiply this by 10 and then take the answer to the nearest millimetre. So that's going to be 126.59, etc., which gets us the answer to the nearest millimetre will be 127 millimetres. Now, wasn't that a nasty little turn of events? Bet a lot of students faulted on that one. Anyway, the answer is 127 to the nearest millimetre. So you've got to keep the story firmly entrenched in your mind as you go and look out for the traps because they're there. Alright, next bit. This is a 2-mark question. And Patricia is also growing tomatoes. Okay, basil, coriander and tomatoes. And she classified these tomatoes as either tall or regular. She finds that 20% of her tomato plants are tall. This is a binomial, guys. P.S. a binomial. A customer, Jack, selects n tomato plants at random and let Q be the probability that at least one of Jack's n tomato plants is tall. Find the minimum value of n so that Q is, what's Q again? The probability that at least one of them is tall, that Q is greater than 0.95. 2-mark question. This is a favourite of VCAA because it's a little bit tricky and it's the hardest thing that you can do in binomial problems. But it isn't that hard. As long as you can formulate a plan of action and then put it into a mathematical equation to solve or inequation to solve, you'll be fine. So just put one foot in front of the other and put down what you know. We know that the probability that none will be tall would be 1 minus q, don't we? We also know that the probability that it'll be tall is 0.20, okay? So that's going to make that 0.8, all right? Now, with a binomial distribution, guys, this is the way I like to do these. You notice we talked about at least one. So let's work out the probability of none being tall and then subtract that from 1, which gets us the probability of at least 1, which is nice and easy. That's what they want to know, whether you have the presence of mind to do. So the probability of none being tall is this baby here, yes? NC none, 0.20 to the none, 0.80 to the n. That's the probability of none being tall, okay? Now this is 1, that's 1, so we've just got 0.8 to the n, all right? Now that's the probability that none are tall. Therefore the probability that at least one will be tall is going to be 1 take away that, okay? And we want that to be greater than 0.95. Now we've got ourselves a nice little inequation to solve, and we're in business, guys. Now, there's a quirk of the TI-CAS handheld that sometimes when you get these situations here, these inequations, it doesn't like solving them. Probably would in this case, but I just don't bother with that anymore. I just solve it when it equals this situation with an equal sign here, and then I test either side of the value of n that I get, the decimal value, decimal approximation value of n that I get. I test the nearest integer either side of the answer and I test which one's right. That's how I do them. I'll show you. So yes, we're solving for 1 minus 0.80 to the n equals 0.95 in the CAS, and then we test values of n integers either side of the result. And this is it. So you solve for this situation equals 0.95 for n, and we've got 13.4 So I'm going to test for n equals 13 and n equals 14, and I'm going to test which one is greater than 0.95. So there's 1 minus 0.8 to the 13, and we get that which is not greater than 0.95, and we get that one there to the 14 which is greater than 0.95, so our answer is going to be 14. And that's they asked us, always look back and check what they actually asked you for. They asked you for the minimum number, so that would be 14, okay? If they asked you just for the number of plants to select, you'd have to say 14 or more, wouldn't you? So you've got to be very, very, very careful the way these questions are worded to get the actual answer nailed completely right, okay? In another section of the nursery, a craftsman makes plant pots. Oh, wouldn't you know? The pots are classified as smooth or rough. Okay. Craftsman finishes each pot before starting the next. Over a period of time, it is found that if one pot is smooth, the probability that the next pot is smooth is conditional probability, guys, is 0.7, while if one pot is rough, the probability the next one is rough is P. Alright, okay. The value of P stays fixed for a week at a time but can vary from week to week. Alright. The first pot made each week is always a smooth pot. Alright, conditional probability, guys. Right, F1. Find in terms of P the probability that the third pot made in a given week is smooth. Alright, now we've got to get our ducks in a row. This is a 2-mark question. If you like, you can draw a tree diagram of it. That might help you get your head clarified as to what to do. But remember that the first pot is always smooth, okay? So that's where you start. The way I've done this, I haven't done a tree diagram. I've said, okay, the third pot is smooth. We always have the first pot is smooth, and the third pot is going to be smooth, so the middle pot could be either rough or smooth. So we've got those two scenarios to deal with, and we can just basically now fill in the probabilities in those things, remembering that they're conditional. So we've got 1 times the probability of a rough given a smooth, times the probability of a smooth given a rough, okay? You got it? This one here is 1 times the probability of a smooth given a smooth times a smooth given a smooth. Now, we've just got to make sure we put the right numbers in here to get our marks. So, rough given smooth was 0.3 and smooth given rough was 1 minus P. If you care to check up there, you'll find that's right. And then this is smooth given smooth was 0.7. Alright, so what is our answer? Looks like that, which if we simplify a little bit more, we're going to get 0.79 minus 0.3 P, and that's our answer for that question. 2 marks for us. Alright, next bit now. In one particular week, the probability that the third pot made is smooth is actually 0.61. Calculate the value of P in this week for 2 marks. Well, we got in the previous question that, didn't we? So if we just make that there equal to 0.61, we got the probability of a third pot being smooth was this, right? If we set that equal to 0.61 and solve it for P, we should be home and hosed. So we solve that with CAS and we get 0.6, no problem. So that's the answer to that one, and P is 0.6. Okay, next bit. If in another week P is actually 0.8, find the probability that the 5th pot made that week is smooth. Well, now guys, tree diagrams become forest diagrams when you get up to the 5th pot or the 4th transition, so it's better to do matrices. So they're actually forcing us to use matrices now, which is no problem for us, a 2-mark question. Let's put our transition matrix in for this scenario where P actually equals 0.8. If you work it out, that's what you will get. Now, what we need is with a initial state matrix of a smooth pot, yes, we need to know how many transitions are we dealing with here, guys. That's the most important thing of all, okay? How many transitions? Get your fingers ready for the counting. We start off with the first pot. Then you go 2, 3, 4, 5. 4 transitions, okay? Not 5 transitions. So that's what we need there, and we can use the CAS for that purpose very, very happily. There it is. There's my matrix defined. There's my initial matrix defined with the smooth pot, and I'm just looking for this little beastie here, and I get that, and we're looking for the probability that the thing is going to be smooth, and therefore there it is, 7/16, exact answer required. And you'll be delighted to know that that's the end of question 4.